Hello guys, so today we are going to discuss about hemoglobin, as you can see. So first of all, we are going to discuss about hemoglobin affinity. Okay, affinity. So first thing we are taking here is oxygen. Whenever oxygen bind with Hb means hemoglobin, okay, we call this hemoglobin as oxyhemoglobin. Okay, and how much the affinity of hemoglobin to carry this? So the affinity of hemoglobin to carry oxygen is 1. Okay, here I am writing affinity. Okay, now if CO2 plus hemoglobin, we call this hemoglobin as carb amino hemoglobin Hb. Okay, and how much the affinity of hemoglobin to carry carbon dioxide? Carbon dioxide is 20. As you can directly see, the affinity of carbon dioxide towards hemoglobin is more. And we all know CO, carbon monoxide plus hemoglobin. What we call this hemoglobin as carboxy hemoglobin. And the affinity of hemoglobin towards carbon monoxide is 200, maximum, the most. Okay, now what is the normal value of hemoglobin in a normal person? So it varies a little bit, like from a male and a female. In male, the normal value of hemoglobin is 14 to 16 gram per deciliter, and in female it's approx 12 to 14 gram per deciliter. Okay, here 14 to 16, and in female is 12 to 14. Now I will tell you how, like if 1 gram of hemoglobin can carry approx 1.34 milliliter of oxygen. Okay, 1 gram of hemoglobin can carry 1.34 milliliter of oxygen. So on an average, if we take the hemoglobin, then we can take it as 15 for both. Okay, so 15 gram of hemoglobin will carry how much? 1.34 multiplied by 15 is how much? Is 20.1 milliliter of O2. Okay, this is 100%. 15 gram of hemoglobin can carry 20.1 milliliter of O2. Okay, maximum. But in reality, artery carry, it carry 19.4 milliliter of oxygen, and veins carry in real approx 15 milliliter of oxygen. Okay, so what we can see from here, and what we can conclude from these values, that saturation is never 100%, or saturation can never be 100%. As you can see, like 20% is the maximum, but still in arteries the maximum person can carry 19.4 milliliter of oxygen, and veins can carry 15 milliliter of oxygen. Okay, so it's approx 97%. So as you know, the saturation can never be 100%. It always move around like 97, like 95, 98, 99, like, but it can never be 100%. Okay, now we are coming to one very important topic, that is oxygen hemoglobin dissociation curve. Oxygen hemoglobin dissociation curve. Now we will discuss this about now. Just imagine this is your y-axis, this is your x-axis. Here we took percent of hemoglobin saturation, and here we took partial pressure. Okay, so just we are going to discuss it here. Just imagine here is the 50. Okay, so the curve which will form in this oxygen hemoglobin dissociation curve is called as sigmoid curve. Okay, and how will this curve look like? This will look like this. Something like this. Okay, like this. Okay, in this curve, just imagine at 25 partial pressure, the percentage of saturation is 50%. Okay, just imagine at the partial pressure of 50, the saturation be like 95%, and at partial pressure of 75, let's took it as 97%, as we know that it can never be reached 100%. Okay, so this is that curve. This point we call as partial pressure. Okay, saturation at this point, the saturation at 50% saturation. Okay, and the partial pressure is 25. Now let's discuss about, in this graph, about left shift or right shift. Okay, let's discuss about them here. In this graph, okay, let's talk about this here. Left shift and right shift in this graph. Okay, so in this left shift, what happened? basically hemoglobin is binding to oxygen. Okay, so what is happening here? Association of hemoglobin to oxygen. O2 means oxygen, Hb means hemoglobin. Okay, so what happens here? The partial pressure of oxygen will increase in your body. Okay, and the partial pressure of carbon dioxide will decrease in your body. 100%. One question will come from this part in your Krok. 101%. Okay, now as we all know, if PO2 is increased in your body, then what will happen? If oxygen will increase, see, in our body carbon dioxide is treated as an acid. Okay, it's treated as an acid. PCO2 is treated as an acid. So in this, what is happening in left shift? Which is increasing? Oxygen and carbon dioxide is decreasing. So what is happening in your body? Alkalosis. Have you got it? Alkalosis. Okay. And what is happening to pH? pH is increases. Okay. If pH decrease means it's going towards acid side. Okay. Like HCl and H2SO4 have pH of 1 and 2. Okay. And bases have more pH. So pH is increases in alkalosis. What is happening to temperature? Obviously, temperature is decreasing. And in this left shift, there is one effect that is occurring, that is Haldane effect. What is this Haldane effect? He was a scientist. Just remember, it's not important from Krok point of view, but just still remember, Haldane is a scientist who find out that in lungs, okay, it's very basic concept, in lungs, oxygen bind to the hemoglobin and carbon dioxide is released out in the air. Okay, so what is happening basically in this Haldane effect? Oxygen is increasing. Okay, he just found out in lungs, like all those processes occurring. Okay, just to remember this, just remember Hall. In Hall, what is happening? There is a big space. Okay, so in big space you can easily get an oxygen. So what is happening? Oxygen is increasing. Now in this left shift, what is happening? 2,3-DPG, or we also call it 2,3-BPG. What the full form is? 2,3-diphosphoglycerate. 2,3-diphosphoglycerate or 2,3-bisphosphoglycerate. Bisphosphoglycerate. Okay, here just bisphosphoglycerate. Okay, what is the function of this thing? Okay, actually, just imagine this is your hemoglobin. It's have an active site. It have an active site. Okay, where oxygen binds. Okay, so what will happen whenever the oxygen binds to it? Here the oxygen binds. It's okay, but when oxygen is not there to bind with the active site, and you know every active site is specific for some specific proteins or some specific molecules. Okay, so hemoglobin active sites are specific for this. Sites are specific for oxygen. They are made for oxygen. So when there is no oxygen, this 2,3-DPG cover this site. When there is no oxygen, okay, to bind from here, this 2,3-DPG cover it like this. Okay, so no other thing can bind it or anything can happen, or nothing will bind it. Okay, so this 2,3-DPG will cover it. So obviously in this, what is happening? PO2 is binding in hemoglobin. Okay, so this will be present in hemoglobin. Obviously no, it decrease. So the 2,3-DPGs decrease in this thing. And one more thing, there is one question I just recently saw. Okay, like in infants, like in child, okay, 2,3-DPG is what? Just in horse, just remember this thing. Okay, in infants, like in small childs, this 2,3-DPG usually is less. 2,3-DPG, diphosphoglycerate, is usually less because their hemoglobin is not very well sensitive to oxygen. Okay, in infants, this 2,3-DPG is less sensitive to hemoglobin. Just write it here if you want to. Like in infants, 2,3-DPG is less sensitive to hemoglobin. Okay, so in them usually it's remain decrease. In infants, it's the main thing. Okay, now come to right shift. During right shift, what will happen? Actually, in this right shift, there is dissociation of oxygen. What is dissociation of oxygen? Okay, so what will happen when oxygen dissociates? So partial pressure of oxygen will decrease, and what will increase? Partial pressure of carbon dioxide will increase. Okay, so what will happen in your body? Acidosis. As I already told you, carbon dioxide is acid for our body. Acidosis, it's respiratory acidosis to be very precise, but just remember here, it's acidosis. Okay, and what will happen to pH? Obviously in acidosis, pH will decrease. What will happen to temperature? Whenever there is acid, what will happen to temperature? Temperature will increase. And here is one effect that we called as Bohr effect. Okay, Bohr is a scientist. Actually, he also finds something like this Haldane effect. Actually, what Bohr find, he find like hemoglobin binding affinity to oxygen is inversely proportional to acidity and concentration of CO2. Hemoglobin binding affinity to oxygen is inversely proportional to acidity and concentration of carbon dioxide. It's very simple. Whenever, okay, I just want to tell you, in Bohr effect, what will happen? CO2 increases. And how it increases? In this effect, what Bohr find out, like whenever the hemoglobin wants to give oxygen to tissue, obviously when it will give oxygen to tissues. Okay, so what will happen? It will give oxygen to tissues and take carbon dioxide and all those products from there and to the lungs. Okay, so that's all he find out. It's very basic thing. And what will happen here to this 2,3-DPG, diphosphoglycerate? What will happen to diphosphoglycerate here? Obviously there is no oxygen or very less oxygen. Then what will happen? It will increases. Because why? Because oxygen is less. Very simple. Okay, how you can remember, like in Hall there is a lot of air coming to you, so lot of oxygen. Okay, in Bohr, okay, Bohr, you know, bore well. If you go down you will suffocate. How you will suffocate? Because there is no oxygen. Why? There is carbon dioxide more. Just mnemonics to remember you. Okay, so that's it. Now let's discuss about this chloride shift. What we are going to discuss about here is chloride shift. What we call this chloride shift? It's also known as Hamburger phenomenon. Okay, what's Hamburger phenomenon? Okay, in this what will happen? Just imagine this is your 1 minute. This is your normal plasma is floating in your cell. Okay, and this is your RBC, your red blood cell. This is your RBC, your red blood cell. Okay, what happens here? See, from tissues, what is coming out? Tissues are giving carbon dioxide. Okay, from tissues carbon dioxide is coming out. Okay, and in this plasma, this carbon dioxides come inside this RBC. This red part is RBC. Okay, your red blood cell. Okay, and this is your normal plasma. When this CO2 come inside, okay, so from this plasma have what? Water. So this from plasma water will enter here. So CO2 plus H2O means water, in the presence of enzyme carbonic anhydrase. Okay, what carbonic anhydrase? It will form H2CO3. What? H2CO3. What is the name of this H2CO3? It is carbonic acid. What? Carbonic acid. Then this H2CO3 will divide in H positive and HCO3 negative. Okay, now what will happen? This HCO3 will come out. And why obviously this will come out? Here there is something called chlorine. Okay, chlorine, when this HCO3 will increase in the cell, this HCO3 okay will increase in the cell, then here are some chlorine channels on the membrane of this RBC. They will open. Okay, so when these chlorine channels will open, it will enter in the RBC, and as a result, to maintain the pH, this HCO3 will come outside in the plasma. Okay, and this HCO3 is the main buffer in our body. Main buffer. Okay, what is the blood pH? It's just a normal question somebody will ask you. I just talk about buffer, that's why I want to mention it here. 7.35 to 7.45 is the normal blood pH. Okay, it's just normal hot thing. This is Hamburger phenomena. And remember one thing, very important thing. In lungs there is reverse chloride shift. Everything in lung is different. Because why? Because for ventilation, in lungs we do ventilation, we remove this carbon dioxide. Okay, here like in this normal state, this carbon dioxide, our body's 85% of our body's carbon dioxide is uses here. About 80 to 85% of our body carbon dioxide is uses here in this Hamburger phenomenon. Okay, but in lungs there is a reverse chloride shift. What happens in lungs? Just opposite of everything that is happening here. Okay, chloride is coming outside of the cell. Okay, HCO3 will go inside the cell. Carbon H2CO, the hydrogen ion and HCO3 will form H2CO3. Everything will go opposite. Okay, now H2CO3 will form CO2 plus H2O, and then CO2 will remove. Okay, in lungs everything